I have tremendous, immense respect, and I enjoy every one of my interactions. And maybe this gives me another avenue to be perhaps even better connected with all the good folks. So let me share my screen and I'll start the presentation. If you have a pressing question, stop me, ask me a question. We'll all learn together. If you want to hold your questions at the end, that's fine as well. So with that said, let me share my.
Yeah, we can see it. Thank you.
Excellent. All right. So, and I do apologize. I'm in full screen, which means that I can't see your raised hand. So if you just prompt me with a voice prompt, I will pause and we can take questions.
Yeah, we'll keep an eye on questions or raise
Excellent.
hands.
So, so today I was going to talk about some of the work we've been doing on analysis of MRIs. Basically, a functional aspects of the operation of the brain. So, functional brain connectomes is what we're looking at, and I'll talk about a number of problems in analysis of connectomes. Um, Basically, the first I'll start off by talking about how you extract features from connectomes, and this has to do with finding signatures in connectomes. So the idea here is just to give you a preview. Let's say I give you your MRI today, and I've given you 100 MRIs 6 months from now. One of those is yours, and these could have been taken on different machines. The question you're asking yourself is, could I tell you which one of those 100 is yours? Could I tell you what you were doing when I took that MRI? Could I tell you how good you are at what you're doing? And not only that, I also want to make sure that I can map that back to regions of the brain or parts of the connectome to get some physiological basis of either your signature or a task signature. So the first part of this talk is about feature extraction. The second part, feature identification. The second part is on feature representation. So in this example, I'll tell you I'll tell you how you would go about looking at MRIs and representing features or extracting combinations of these attributes that I talked about in the first part. So the challenge here is that there are a bunch of people who are sitting in an MRI machine watching a movie. In this case, it's the first episode of the BBC show Sherlock. And I'm going to record all of their MRIs, and I'm somehow going to extract features from those MRIs so that those features are strongly correlated with some features in the video itself. And I'll show you how we go about doing that. And the third one is the most ambitious of these, and in fact, it's actually not even published yet. But this is, can I look at your MRIs as you're watching and listening to something, and can I reconstruct this? So this is truly mind reading in some sense. So these are three topics I'll talk about. I'll mix both methods and statistics and application. And time permitting, I'll actually spill over this presentation and we'll talk some more about in depth about the methods that we develop and use here. So I know that many of us may not be deep into connectomics, so let me just give a quick and dirty of what connectomics really means, at least in the context of what we're talking about. So what is a connectome? Connectome is a map of the brain, and the map could be structural or functional. In other words, as the name would suggest, it's connection between something. The connection could be physical, or the connection could be functional. So what I mean by that is physical connection could actually be fiber tracts that connect different parts of your region, of your brain. And it could be functional. In other words, that you're actually doing something and I'm recording some activity in your brain. And I'm trying to find out when two parts of the brain have highly correlated, demonstrate highly correlated activity. So think of these as recording a time series from two different parts of the brain. And we're looking to see when those two time series are highly correlated, in which case I would say that those two regions of the brain have something to do with each other as it relates to the task that you're performing. So you may see that you can have multiple representations of these. So the both structural functional connectome, you can think of these as matrices. And very often you don't do this at a voxel scale, you do this in a brain area scale. So I can take your MRI, I'll show you how to pre-process this, but I can basically identify areas of your brain, and I can define an area by area matrix. and where it lights up is where I would say there's either structural connection or functional connection. So this is how we're going to look at this data. For the most part, we're going to focus on functional connectomes here. And as I mentioned, functional connectomes measure coherence in neuronal firing at rest or while performing a task. We're not going to look at structural connectomes. Structural connectomes are often called wiring diagrams. They're physical in nature. Uh, there are significant interesting questions that you could ask on the correlation between the functional and structural connectomes as well. This is work we're doing right now, but it's not something we're at a point where we have good results that we can share. So for this talk, I'll mostly stay with functional connectomes. And as I mentioned, what you're really looking at is a matrix, roughly region by region matrix. And here's a heat map of the correlations. And this is the matrix that provides me the basis of a lot of analysis that we're going to do here. Right. So before we do any analysis, as you may imagine, you have to do a whole bunch of pre-processing to your images before you can get to a clean data structure that I mentioned. So the way you think about an MRI, it's of course it's 3D plus time. So we're getting 3D images in time, roughly at about 1 second interval. So we're talking about a 1 hertz frequency here. The 3D images are themselves roughly about a millimeter cube in resolution. So you're thinking roughly, if you think of your MRI volume as about being, say, 20 centimeters by 20 centimeters by 20 centimeters, that's your volume. Then the spatial resolution in each dimension is about a millimeter, and the temporal dimension is about a second. The first problem that you will deal with is that this is a very noisy functional image. So the first thing you have to do is distortion correction. Nobody sits still in an MRI machine, which means that our head's moving a little bit. So you have to do head motion correction. We're not necessarily interested in the skull or the water, so we have to do skull stripping. So we take away all the voxels from your images that have to do with the skull. Then using a structural image in a standard brain, we normalize and register. What that means is all of our brains are slightly different. They're different in size, and our anatomical regions are different as well. And to be able to do a canonical analysis, I first have to standardize them. So we use a standard brain called MNI. And so we stretch and turn the brain in such a way that the brain is then aligned with MNI. And at this point, the brain is normalized and registered. And what I get from that point on is a processed functional image. Of course, I still have to do more processing on it because I have to register it with an atlas, and I'll briefly mention that when we start talking about this. So let's get to our first question. And the first question is, do brain signatures exist? In other words, are there parts of your and my brain that are unique to us? We call these signatures. So brain signatures are signals in the connectome that code for individual level uniqueness. And you can think of brain signatures as fingerprints. And there's been a lot of work showing that brain signatures do in fact exist, not in an explicit sense, but in a sense that if you give me this processed image for you and you give me, remember the 100 images 6 months later, 99 of those are not yours, one of those is yours, with more than a 95% accuracy, I can identify which brain is yours. And there have been a number of results leading up to ours, which say that such signatures exist. Most notable, if you're interested, is a paper by Emily Finn, which appeared in Nature Neuroscience, which basically uses raw correlations to tell you that such signatures exist, and you can get a relatively high accuracy in being able to predict which one of the MRIs is yours, but it doesn't say anything about where that unique aspect of your brain actually lies. So the first key question that we're looking to answer is what part of the functional connectome is unique to individuals, and we call them brain signatures. All right, so the problem is set up as follows. On day one, we have a bunch of people who have taken their MRIs, and on day K, on some other machine, there's perhaps the same or perhaps even a different set of people who've taken their MRIs. And the question is, can we find corresponding entries across these things? And we want to do that in a way that actually maps back to the connectome and tells us something about what part of the brain defines our unique aspects. All right, so here are the questions we're going to look to answer. Can we find connectomic markers for individuals based simply on their connectomes? The next question, if you can find individual specific markers, can we find task specific markers? So now you're in an fMRI machine, you're doing a motor task, you're doing emotional processing, you're gambling. Could I find out what are the parts of the brain that light up when you're doing these specific tasks? Can we characterize how well people perform at these tasks? So if you were gambling and let's say in one round you won, another round you lost, could I predict when you won and lost? Can we find signatures that are encoded exclusively in the functional connectome as opposed to the structural connectome? So I'm not really interested in the structural or anatomical uniqueness. I'm really more interested in our processing uniqueness or the functional aspects that are unique to us. All right. So as I mentioned, existing methods do not prescribe spatially localized markers and lack anatomical basis. So while Emily Finn will tell you that with 95% accuracy, a specific MRI 6 months later is the one that is yours, that prediction says nothing about why it is yours. In other words, what part of the connectome uniquely identified you. So our goal is to find localized regions in the brain that code for identity. And the idea here is actually neat, elegant, and simple. We use what are called leverage scores to sample a very small set of discriminating features. And we show that just using that small set of discriminating features, I can identify people with the same accuracy as any other method, perhaps actually slightly better. Given that the earlier methods were already about 95, 96% accuracy, we show marginally better, 97% accuracy or thereabouts in identifying who you are. So we use leverage scores for connectomes on day 1 to select features that are strongly correlated in corresponding image on day k. So let me explain what leverage scores are. Let me explain the process for it, and then I explain what leverage scores are. So here's what I'm going to do. I'm going to take each of the n subjects on either on day 1 or on task 1, let's say, and I'm going to take the correlation matrices, and I'm just going to stack them up into a vector. So I vectorize all of these matrices. I vectorize all of the correlation matrices. And so this gives me a matrix of this kind where each column corresponds to one subject. So now I have this matrix. And what I'm trying to find out is what rows in this matrix. In other words, remember, a row in this matrix now corresponds to one entry in this connectome. Okay? So I'm asking myself the question, what rows in this matrix capture most of the distance in this matrix? So if you think of matrices, and let's call this matrix A, then if you think of the matrix A transpose A, remember the matrix A transpose A is really the dot product of column I and column J, okay? So you can always think of A transpose A as the distance, the ijth entry of A transpose A is the distance between entity I and entity J. So now, I can give you a sense of what leverage score sampling would do, and I'll give you the math of that. So let's say I've given you this particular matrix, and I'm interested in the distance between columns of this matrix. And now I'm asking you this question, give me a very small subset of rows in this matrix that best preserves the distance between these columns, okay? And that's what leverage score does. And in fact, if you were thinking ahead of me, what leverage score does is it'll take the matrix A, it'll compute A transpose A. There's a reduced matrix which only contains a subset of these rows. Let's call that matrix A prime. And so now you have A transpose A, and you have A prime transpose A prime. So A prime transpose A prime is the distance in the reduced row space. A transpose A is the distance in the complete row space. And we're somehow trying to find a subset of rows such that the difference between these two distances is minimized. And there are some proofs, these predate us, that leverage scores do this, and I'll briefly show you how they do this. So, but the bottom line is I'm going to take this matrix and I'm going to do leverage score sampling. And what leverage score sampling will do is to give me a much smaller set of these rows with the property that if I simply consider these rows, the distances in this submatrix best approximates the distance in the whole matrix. Okay, so I've given you this magic box for now. So I'm going to take this matrix, I'm going to do leverage score sampling. I'm going to do that on day 1 and day k, or on task 1 and task 2. And now I'm going to compute the correlation not on the entire matrix, but only on the subsample matrix. Okay, so I'm doing this in a much reduced space. And now I get a correlation matrix. And I'm going to use this correlation matrix to predict what task you're doing or who you are. And if I can get the same kind of accuracy in this reduced space, then basically what that tells me is that this reduced space of rows is your signature. It is what distinguishes you from everybody else. So this is the big setup of this part of our problem. The only thing I haven't told you is how I do leverage score sampling and what kind of results I get from this. All right. So this is not our work. This predates us. We just happened to find this and use this, which worked very well for us. So leverage scores work as follows. If I'm given an arbitrary n by d matrix A, n is much greater than d in our case. Let's say you've computed an SPD of this matrix, and let U denote the left singular vectors of A. Okay. I'm going to take one row of these left singular vectors. And so UI denotes the ith row of the matrix U. So I've taken all the left singular vectors and I've stacked this into a matrix U, and I'm only considering the ith row of this particular vector. Then basically you can think of the importance of that particular row as the norm of the vector. In other words, in the left singular vector, the rows with the most power are the most important ones when it comes to leverage score sampling. And in fact, this is not very complicated. There's actually a nice proof that in expectation, A transpose A minus reduced A transpose reduced A in the Frobenius norm, this error can be bounded quite nicely. Okay, so the algorithm is quite simple. I'm going to sample rows with probability that is proportional to the 2 norm of the ith row of the left singular vectors of that particular matrix. Okay, there's a probabilistic version of it and there's a deterministic version of it. The probabilistic version simply samples with this probability. The deterministic version simply sorts by this particular norm and picks the rows that are most important with respect to this particular norm. All right, so how well does this work? So here's a data set from the Human Connectome project. It's got functional MRI. It's got the functional MRIs include resting as well as 7 tasks. It's also got EEGs and MEGs. We don't use EEGs and MEGs for this particular experiment. We are only going to use the functional MRIs from the unrelated subset of subjects. There are confounding effects when that happen because of twins and related subjects, so we're not looking at those confounding effects. The data acquisition for this particular data set is done over 2 days. On day 1, the subject is performing resting state fMRI, followed by 4 tasks: language, emotion, gambling, and motor. The second session happens 2 weeks later. So on day 15, once again, there's 1 resting state fMRI session, followed by relational, social, and working memory tasks. So this is the whole data set that we're working with. And once again, there are about 1,100 subjects in this data set. So the first hypothesis that I'm going to show you is that a very small number of features actually code individual identity. So we're not doing this at the level of voxels here. Remember, your raw, your processed MRIs got about a very large number of voxels. We're talking something along the lines of 600 by 600 by 600 voxels. In fact, what you do is that once we've registered the MRI or the brain to MNI, then we can use what is called an atlas. An atlas basically segments the brain into a small number of regions. And we use an atlas to reduce the brain to roughly about 360 regions. And once you reduce the brain to 360 regions, the connectome is not defined on a per voxel basis, it's defined on a per region basis. And the way we do that is we take all the voxels within a region, we average them, and now our matrix has become a region by region matrix. And that's roughly about 64,000 entries. So there are 64,000 edges in this graph, if you will. And we're only picking a very small number of regions from this graph. So we're only picking 60 edges out of 64. And we show that as few as 60 edges in this connectome accurately predict the corresponding identities in day K. And this is incredible. So a very, very small fraction of the brain almost uniquely determines who we are. And then, like I said, the accuracy ends up being about 95%, 95 to 97%. And that accuracy is the peak of what Emily Finn shows using the entire brain. So the key result here is that a very, very small number of features code for really who we are. And the beautiful thing is, remember, those edges actually map to regions of the brain. So we can actually do an anatomical mapping of individual specific signatures. So as I mentioned, each feature is an entry in the correlation matrix, which means that it represents a similarity between two regions of your brain. So we do want high confidence regions. So we find high leverage scores for different randomly selected subsets of subjects. And then we retain the features which occur in a statistically significantly large number. So we pick a p-value cutoff of 10 to the power minus 10. So that's very statistically significant. And we find that regions with high leverage scores are really clustered in very localized regions of the brain. In fact, in this case, it happens that it's in the parietal and the prefrontal cortex, which really has to do with cognitive processing. And this is beautiful. What it says is that the way we think uniquely defines who we are. So this was a very cool result. I believe this result is in this year or last year's Frontiers in Neuroscience. So
Ananth, you have a question.
Please.
So Fatima, do you want to ask the question?
Sure. I just had a quick question as to since these signatures are based on functional connectomes, I was wondering, in an individual, can these functional connectomes evolve with time or throughout lifetime?
Oh, absolutely. So this is something we are doing at this point. So we just got a new data set of, I believe, 130 patients, ages 18 to 80. And so this is a really cool data set. And so they absolutely evolve. They evolve naturally. They also evolve in response to trauma. They also evolve in response to disease. They also evolve in response to neuroplasticity. So if you were to have, for example, or one were to have TBI, traumatic brain injury, the brain recovers a lot of the function, and that's neuroplasticity. And so right now we're actually trying to characterize exactly what happens with age, what happens with disease. In fact, I think we should have this data set soon from Gilead. And this is imaging in response to COVID. And so there, the hypothesis is that when patients present early with cognitive deficits in COVID, that their long-term prognosis is actually a lot worse. And so we're just in the process of signing a whole bunch of paperwork to get that data set. So that's an excellent question. That is a beautiful set of research questions that are completely unanswered. Send me an email. I can tell you what those data sets are that we're looking to get. These are relatively public data sets, but you still have to go through a process to get those data sets. But there are a number of cool questions you can ask on what is the natural evolution of these connectomes, how they respond to disease, how they respond to injury, things like that.
Thank you.
So continuing, the next question you ask yourself is that if we uniquely identify ourselves in terms of our resting state fMRIs, can we also identify signatures for tasks? In other words, if I'm doing language processing or emotion processing or gambling, are there unique parts of our brain that light up together? So we can do exactly the same procedure. Instead of doing day 1 and day k, we're actually doing this in terms of tasks. So we do the same procedure in task data. For each task, we use the first half of the session to find features and predict on the second part of each session. So this gives us a task-specific signature, and that we find that prediction accuracy is generally very high. There are a couple of tasks, specifically motor and working memory, where we don't have very good accuracy. But for all the other tasks, the accuracies are in the range of 70 to 80, or perhaps even beyond 90%. And what that says is that if you're doing something, I can tell you exactly which part of your brain are going to light up, and that those parts of the brain are actually invariant across us. In other words, what lights up for you is exactly what lights up for me as well. So you might ask the question, why are motor and working memory not giving us good accuracy? And the hypothesis here is that they actually combine different parts of the brain. So a motor has to also do with some visual processing. It also has to do with reflex. So there are different parts of the brain that all come together, different stages of motor processing. And that's why when you average over these things, we don't actually get a good time signal. But that's not to say that there's something fundamental about these. It just says that this particular method does not give us good accuracy on motor and working memory. If we were to take a segmented version of these time series, we should be able to increase the prediction accuracy and the signature accuracy of these tasks much higher as well. So of course, you would ask the next question. Oh, by the way, there's a cool thing here as well. You might ask the question, do markers of a task code for identity even when the subjects are performing a different task? So let's say on day one, you were doing language, and on day K, you were doing gambling, or you were gambling. Could I use the markers for language to predict who you are, even though you were gambling at your second session? And we find that markers for a task, you find markers for one task, and you use it to predict identities when performing different tasks. And you actually get good accuracies even in that case. We observe that resting state markers are indeed the best, but in fact, you can actually use task-oriented markers to identify individuals, and they work relatively well as well. So this is another hypothesis in question you can validate. The final hypothesis that we validate here is, can you get a sense of task performance from these fMRIs as well? So in this final result, we predict the efficacy using a relatively simple regression model that we fit using support vectors. So the regression model uses support vectors and predicts the performance metrics for a test set. The model is built on a train set. And it turns out you can actually train a model quite well on a train set, but you get excellent accuracies on the test set as well. So this is really cool. We've gotten to a point where what I'm saying is, I can take your fMRI, I can actually identify who you are, I can identify what you're doing, and I can identify how good you are for the most part at what you're doing. All right, so let's now move on to something slightly more aggressive and ambitious here. So now I'm asking the question, let's say I subject you to naturalistic stimuli. So, viewing a movie, listening to an audiobook, these are all considered naturalistic stimuli. Is there something I can learn from your neuronal response that says something about the stimuli? Or conversely, if you give me a stimuli, can I predict what kind of neuronal response I'm going to get from that stimuli? You may ask a number of other questions as well. How similar is our neuronal response to the same input? In other words, if you and I are watching exactly the same thing, do the same parts of our brain light up? How similar is our neural activity when we recall from memory? So in other words, you watch Sherlock, and now I'm forcing you to recall certain parts of that particular show. Will the same parts of the brain light up? How similar are responses to the same movie, but in different languages? So many of us are bilingual. So let's say you watch Sherlock in English and the same episode of Sherlock in French. Do the same parts of the brain light up for the most part? So these are really cool questions you can ask, and we answer some of these questions in the next study that I'm going to show. But a number of these questions still remain, and if you guys are interested, I'm happy to share with you what we have not answered as opposed to what we've answered. All right. So here, the key is as follows. So the goal is to find representations for a given fMRI that is consistent across subjects. In other words, I'm trying to extract something from our connectome that is similar to you and I as we watch the same show. And we want these representations to also capture something about what we're watching. In other words, what is common to your and my brain as we watch the same thing? And can I correlate what I'm extracting with what we're watching? And here we use a slightly different matrix technique, and this is called archetypal analysis. All right, so archetypal analysis is actually very cool. We find ourselves using this in many, many different areas. So let's say I've given you a matrix once again. This is the matrix of responses. I'll show you how we construct this matrix. For now, somehow you have constructed a matrix from the fMRIs. And I want to break this matrix as a product of two other matrices. So this notion of matrix factorization is everywhere, right? So you can, in the base case, you can think of clustering as matrix factorization. So the way you think of clustering as matrix factorization is that, think of each row as a data point and the cluster centers as being representative of these data points. And now in the factorization, the first matrix is the cluster centers, and the second matrix is the extent to which each point draws from each of those cluster centers. So you can express each point as a linear combination of those cluster centers. So you can think of clustering, for example, as matrix decomposition. But there are many other matrix decompositions. We use a matrix decomposition called archetypal analysis, and this is actually kind of cool. So conceptually, the way to think about archetypal analysis is think of a bunch of points in very high dimensional space. In this case, let's say 30,000 dimensional space, and think of the extremal points as being archetypes. So now I've said, hey, give me the best convex hull in this 30-dimensional space that encloses as many points as possible. So the key goal is to now find the convex hull in this 30-dimensional space, with the understanding that every point on the inside of this convex hull can be represented as a convex combination. So convex combination simply means it's a linear combination that is all positive and sums to 1. In other words, if I've given you a convex hull of 5 points, then every point on the inside is, let's say, 0.1 times the first point plus 0.8 times the second point plus 0.05 times the third point, and so on. So basically it sums to 1, it's all positive. And this is kind of cool because it has a really nice intuitive explanation to it, because the archetypes are the extremal points in my data space, and everything else is a convex combination, which means that I can interpret this. You are 0.8 of the first archetype, 0.1 of the second archetype. So there's a very natural explanation that derives from these archetypes. So once again, mathematically, the optimization procedure is as follows. You minimize over matrices C and S such that X minus this product of 3 matrices X times C times S in the Frobenius norm is minimized. As I mentioned here, there are 2 convex combinations here. The archetypes themselves are convex combinations of data points, and the data points are convex combinations of the archetypes. So S is really the coefficients that I was talking about, 0.8, 0.1, and so on. So in this case, this shows that this constraint corresponds to the convexity. In other words, they must all be positive and sum to 1. And also, since the archetypes themselves are convex combinations of data points, the matrix C itself has a convexity constraint on it. In other words, it's all greater than 0, and it sums to 1. So once again, the matrix XC is the extremal points. This represents the convex hull or the archetypes. And the column J of S represents the fractions of all archetypes, which explain data points J. So it's a very clean, intuitive representation. Now with this hammer, I'm going to see what I can learn about my videos that I'm watching. So here's what I'm going to do. I'm going to take the episode of Sherlock. So once again, this data set is about 30 odd people watching the first episode of the BBC show Sherlock. So I'm going to take this BBC show, and I'm going to divide this into divide the episode into scenes. And actually, this is done by a third party. We don't have to work too hard to do this. Each scene corresponds to roughly a few tenths of MRI frames. So think of this as few tenths of seconds. So this is just movie scenes. There's nothing deep about this. So then I'm going to stack all the fMRI frames that correspond to one scene from all subjects into a matrix. And I'm going to do archetypal analysis. So as I mentioned, archetypes are representative snapshots of brains corresponding to the scene. So if I find all the corner points, basically what I'm going to get is what are the archetypes of neuronal responses as I'm watching each scene. Now for each fMRI frame, for each subject, I'm going to find the closest archetype. And then I'm going to find the consensus archetype for each frame. In other words, if most of us map to one archetype, I'm going to say that that archetype represents the neuronal response in response to subjects watching that scene. And we call this the dominant archetype for that particular frame. The set of dominant archetypes corresponding to each time frame forms a canonical representation of that particular scene. So this is really cool. So now I've taken you from the space of fMRIs to something that I'm deriving from the fMRIs that represents the scene. So pictorially, this is the process. I'm going to take, for each subject, I'm going to take the entire episode, and I'm going to break this up scene by scene. And for each of these scenes, I'm going to extract the fMRIs. I'm going to stack those all together into a matrix, and I'm going to compute the archetypes for each of the subjects. And from there, I'm going to compute the consensus, and I'm going to derive what I'm going to call the dominant archetypes that correspond to each scene. At this point, it's
Ananth, I have a very strange question given
ask away,
that you're
please.
talking about. So, could this technique be used for, criminals or like some very,
So here,
malicious activities as well?
absolutely. So one of the big ways to use this is behavioral characterization. So I'm not, let's not talk criminal law, but nevertheless. So you can actually, there is evidence to show that these kinds of, not specifically these mathematical techniques, but that there are techniques that can be used for behavioral characterization as well. And also you can extend these beyond behavioral characterization to also behavioral deficits. So we can absolutely do this.
Got it. Thank you.
All right. So here's the data set. Actually, I was wrong. There's 17 subjects in this study, so 30 might have been in the next study. So the data set here is subjects viewing an episode of the first episode of Sherlock. There were 17 subjects, approximately 50 minutes of viewing. I've seen the entire show. It's a very nice show if you haven't watched that, the BBC show. So the first episode is roughly 50 minutes. There are about 2,000 fMRI frames, and there are roughly 50 scenes. This is not our annotation. This is expert annotations. We use the regions of interest from the hippocampus and the dorsal default mode network. These are also well known, and they're associated with visual processing and auditory processing. As I mentioned, hippocampus is also implicated in episodic memory, and the dorsal default mode network is active for viewing stimuli. So we don't work with the entire brain. We only work with these regions of the brain. All right, so is this all smoke and mirrors, or is there something real? So the first thing you ask yourself is similarity in the space of my archetypes saying anything about the similarity in the space of annotations of the episode itself? And we don't do the annotations. So the goal here is to validate that frames with similar or same archetypes are actually similar in terms of the episode itself. So the way we show this is we find pairwise archetype similarity of frames. And this is in the leftmost heat map that you see. We also calculate pairwise annotation similarity, and we don't do the annotations. So these annotations are done by experts on the basis of excitement, emotion, indoor, outdoors. There's a whole bunch of attributes here. So we take those vectors of those attributes and we compute the dot product of those vectors. And this is in the middle heat map. This is the frame-wise similarity of expert annotations. And really the proof here is that if there's strong correlation between the leftmost matrix and the middle matrix, then basically what I've shown you is that what is similar in the archetypal space is also going to be similar in the audiovisual space of annotations of the episode itself. And sure enough, we show that you get very, very statistically significant correlations between the left heat map and the right heat and the middle heat map. So that's the right heat map I'm showing you. This is the frame-wise similarity of archetypes and annotations. So this is very cool. This actually shows you that the archetypes that we're drawing from the scenes really, and remember, the archetypes are drawn from your neuronal response. They have nothing to do with annotations of the episode itself. So the left is neuronal response. The middle is the episode. And what I've shown you in the right is that they're very statistically strongly correlated with each other, which basically says that what I'm drawing from the brain is actually very strongly correlated with what is on the episodes. So we can actually also, these are also
I have another question.
Please.
Can I ask another question? Sorry, you said we can interrupt.
Oh, actually, Gabriela, please feel free. It's good to make it a conversation.
So one thing I'm thinking, what other applications could be beneficial? Is this like education to me? Like kids have different interests and so forth. Sometimes they cannot necessarily express them directly. Would this be some way in which you can kind of direct knowledge in a particular way so that they enjoy it more? And
absolutely. So let me give you the applications that we have been working with some people on both the first part and the second part, and I'll come to the third part of the talk later. So the first part of the talk was really on understanding what we are doing from what we are measuring, right? In other words, task characterization, how good we are at what we're doing. So we're actually working with two companies on that. So one is BMW, and apparently in Europe, you're really not allowed to put cameras in cars. So what we're looking, or what BMW is looking to do, is to put EEGs inside the headrest of 7 Series BMWs. And so you pull the signals from EEGs, and so they're talking to us to see how much we can learn from the EEGs on operator state. In other words, is the driver falling asleep? Is the driver doing something else other than driving? So that's one specific interest of BMWs. The problems there are a little different. We can go into more detail. EEG has much more temporal resolution, so you get kilohertz signals, but it has much poorer spatial resolution. So you only get about 16 or 32 channel inputs. Uh, MRIs, on the other hand, have very high spatial resolution, but very poor temporal resolution. So there's still some challenges that we're looking at with BMW. We're also working with Procter and Gamble, and their interest is in sleep studies. So are there little Bluetooth-enabled EEG sensors that you can stick on your head while you go to sleep? And can you get a very good sense of how we can characterize your sleep? There's actually if you're interested, there's a nice data set called the Sweden Sleep Study. And these are MRIs of people that are sleeping. And you can actually characterize very different kinds of sleeps and how you transition across those different kinds of sleep. So it's, think your Apple Watch on massive steroids that you can do. So those are all examples of what you can do on task characterization. There was actually a program at DARPA that we didn't compete for, where DARPA recognizes that the main bottleneck on these advanced fighters is actually motor response. So we can think very quickly, but the speed with which we move our hands is actually the bottleneck, not so much our thought process. So they're actually looking at modalities, helmet-mounted modalities, where in fact you learn what I'm thinking and use that to directly affect control, as opposed to going through a motor response. So there are really cool applications on the first part of the talk. The second part of the talk is you can design audiovisual stimulus to get very specific responses in your brain. So, for example, if you want this notion of happiness, how do I design a scene that optimally gives you happiness? And that's exactly the predictive part that I'm talking about here. So I can actually design an entire episode, whereas you say, I want children to have exactly these kinds of responses in the brain. I can design that stimulus by saying, hey, instead of staying indoors, let's be outdoors. Instead of having sky as a backdrop, let's have green as a backdrop. And these are all things that elicit specific responses. So, Gabrielle, you're spot on. That's exactly the application we think of in doing this.
Nice, thank you.
So to that point exactly, how predictive are these things? So in this experiment, we hold out 30% subjects and train on the remaining. We use frame-wise dominant archetypes of the train set to measure how well we can predict the frame-wise response on the test set. In other words, can I predict how you are going to respond to a particular scene is what we're talking about. So here we show that 77% of the test set frames are closer to the corresponding dominant archetypes as opposed to any of the other archetypes. So what that means is, let's say you were happy watching a certain episode, then I can with high accuracy say that somebody else watching that same episode at that time will have a very similar response to this particular archetype. And on the flip side, the root mean square error is 20% with respect to the dominant archetype, and on average 45% with respect to other archetypes. In other words, that I'm much closer to your archetype than I am to all the other archetypes. So what that means is that I can actually predict people's responses quite accurately using these techniques. So this is actually kind of cool. So it's got fun stuff that you can do with this. The other question you might ask, once again, is how stable are these representations? And we show that these representations are actually very stable across individuals. So archetypal analysis on all scene-wise population matrices gives us a very stable representations, in the sense that, in this case, 93.32% of all time frames in each epoch were consistently closer to the same archetypes across all subjects. In other words, all of us will demonstrate the same behavior. It's not that we have averaged something and we're using averages to play games here. No, we will all gravitate towards the same response pattern for all of these scenes, which is actually very, very cool. So this is a cool set of results. This particular work appeared in HCI last year, I believe. So you can look that paper up if you're interested. So the idea here is that we show a really neat approach to deconvolving responses from a population, from functional images of populations. We show that the deconvolution gives you a very stable and finely resolved frame-wise representation of brain activity. And that we show that these representations correlate very strongly with frame-wise annotations, and that they can be used to predict responses in new subjects who are shown the same stimulus. So they have really cool applications on designing specific stimuli. All right, so now we get to the really ambitious part of this talk, which is can I read your mind? So now the experiment is as follows. So up until now, we've shown that complex dynamic responses to continuous visual inputs can be represented in low rank or archetypal representations. And what we'll show now is that we can actually predict objects that you're watching on the screen. So in this particular case, we can say, for example, that you're actually watching a face or a car or outdoors, things like that. And we can do that quite well. And that we can reconstruct individual video frames from your fMRI. So this is really cool. So you're in an MRI machine, you're watching a movie, I'm looking at your MRI, and I'm actually telling you what it is I think that you're watching. So basically this combines the attributes that we've drawn from the first part, the representations we've drawn from the second part, and a whole bunch of deep learning architectures that we built to do the reconstruction and prediction. All right, so here is the high level approach. We divide the video inputs into train and test sets. We train an encoder decoder neural network on this training video clips. Okay, so the idea here is that I'm not going to do this in the space of the entire image. I'm going to do this in some latent space. So I'm going to train an autoencoder. I'm going to squeeze the autoencoder in the middle, so I have a relatively compact latent representation. And what I'm going to do is to try to predict that latent representation. And if I can predict that latent representation, then I can use a decoder to actually do full reconstruction. So we use the trained encoder to convert video frames into latent representations. Separately, we train a map from the fMRI response to the latent space. So I'm going to show you the visual, but think of it this way. We have an encoder-decoder framework trained, and separately we're coming in from the fMRI into that latent space as well. So now you can go to the decoder from two places. You can either come from the encoder, or you can come from the fMRI into the decoder as well. And we reconstruct video frames from fMRI using the previously trained map and the decoder. So this is the big picture. So think of it this way: there's a video coming in, there's the encoder and the decoders. In the middle is the latent space. Now separately, I also have the fMRIs of the people who are watching the same video. Of course, there's these alignment issues, and there's the issue of time skew, and there's the issue of temporal resolution, but we take care of all of that. But modulo all of that, we then train a function that maps my processed fMRI into the space of latent vectors as well. So you can think of multiple paths here. The first path is simply from the encoder through the decoder back to the video itself, or I can come from the fMRI into this latent space and into the decoder to do the reconstruction. So this is pretty cool. And the encoder decoders are not particularly complicated. So, you take your input and there's a whole bunch of pooling and convolution layers. You flatten it and you run it through an RNN at the back end, simply a GRU. And that's the encoder. And there's a pinch point here, which is a latent representation. And then there's the inverse convolution followed by the whole bunch of upsampling stages, which will get you your video back. And the latent representation, in fact, is quite small. It's only 1024 by 1. So we're talking about a very small latent representation in this particular case. So this is the encoder-decoder architecture, and this is the fMRI to latent map architecture. So there's a whole bunch of GRUs followed by some dense layers, and that gets us into the latent representation as well. So with this, we can start to show a number of things. So we first showed that the cluster structure of predicted latent vectors from the fMRI is very similar to the latent vectors that you would get coming in from the video. Remember, you can come to the latent space from two places. You can either come from the video itself or you can come from the fMRI. What we show is that you will get to roughly the same places, whether you come directly from the video or you come from the fMRI. So what basically this shows is that the output of the map is a good approximation to the output of the encoder. And what this does is it allows us to make really cool predictions on what it is that you're actually watching. It also allows us to do reconstruction by simply going from fMRI to the latent space through the decoder. All right, how do we do this? We train the encoder decoder and the fMRI latent map as we've described earlier. And basically this gives you three things. This gives you latent vectors corresponding to the train set within each iteration of cross-validation. It also gives you latent vectors in the holdout set in the training procedure of the nonlinear map. And it gives you latent vectors of the test video and the corresponding test fMRI. So now for the first validation, you can basically cluster the outputs of the encoder and the map separately. And let's say you picked a whole number of clusters, anywhere from, we try k equals 3 to 20. And then you compute an ARI between these two clusters and see if you get good ARIs. In other words, are the clusters that you get coming from the MRIs very similar to the clusters that you would get coming from the original video itself? All right. So this is the first cool representation. So this is a visualization of the latent representations computed from as you're coming from either the video or you're coming from the fMRI. And this is actually a t-SNE plot. So these are in high dimensions. This is mapped to a two-dimensional plot using t-SNE. So the blues are when you come from the fMRI. The reds are when you come from the video. And this is beautiful. We were shocked by how cool this clustering is. And what this tells you is that we can get to very close to the same latent points, whether you come from the original video. In other words, I knew what you were watching, or I didn't know what you were watching, but I knew your MRI. So I could get to basically that same spot in your latent space from these two places. So this is a good validation. But numerically speaking, what we also see is that the ARI is actually very, very good, even for, even as you increase the number of clusters to a very large number. So even up to 20 clusters or so, you get very, very good ARIs for these things, which basically tell you that we can predict the latent space very well from the fMRIs. So basically the high values of both measures show that embeddings obtained from the two routes are very similar. And you conclude from this that fMRI processed using the training map can be used to approximate the video frames and the encoder. You will note that once you get to very high values of K, the measure does actually plateau, but that is somewhat to be expected for multiple reasons. Of course, we're talking about a training procedure that is or the training set that is very, very weakly sampled. So we don't have a very large number of videos here. So if we had a much better set of much larger set of training videos and a diverse set of training videos, we would be able to scale K much, much larger. And of course, we haven't hyper-tuned the deep learning models themselves. So I'm sure there's more juice here to be gained from tuning the deep learning models. So now let me show you the second validation. So now what we're going to do is, remember, you can come in on the red dots or you can come in on the blue dots. So what I'm going to do is to come through the blue dots. In other words, I don't have the original video available to you. I only have the MRIs available to you. So I'm going to come through the blue dots, but I'm going to move the blue dots to the closest red dot that I have in my training set. And then from that red dot, I'm now going to decode that through the decoder. And I'm going to show you what I think you're watching using something that I've seen before. In other words, I have your fMRI of something that you're watching that I don't know what you're watching, but using that fMRI, I'm going to predict that is very similar to something in my training set. Okay, so this is the experiment that we're watching. So I skipped a slide just in the interest of showing you the pictures. So here, the left panel is what the original image was, but I don't know that. All I know is the MRI response in response to you watching that left video. So I take that MRI and I move that I find the blue dot in my latent space. I move that blue dot to the closest red dot, which means that, hey, just show me something in my train set that is closest to what this might be corresponding to. And then I take that red dot and I move that red dot through the decoder. And that's the image on the right. Okay. So think of this as what is closest in my visual library that is closest to what I think you're watching. And this is really, really cool. So you see a building and some sky, and you see a building and some sky with something hanging. In fact, it even picks out what looks like a flag here. There's a gentleman here, the face of a gentleman here. You see the face of a gentleman here. You see somebody's hand, and you see somebody's hand from the training set. This is a sky and perhaps some trees in the sky, and the same thing. The gentleman wearing a hat again. This is some other gentleman with a head covering. Seen from a rural scene, seen from a rural scene. So this is really, and these are just examples, but these are not cherry picked. I'll give you more examples of reconstructions. This is very typical. And in fact, if I had a much better training set, these would be even closer. But this almost freaked us out on how cool this is in what I can pick from my library or what I've seen that is very, very similar to what I think you've actually been watching. All right. So now is the really hardest part, which is I'm going to do full-blown reconstruction. So here is your video. On the left is I start from the video, I can go through the encoder, I could decode this, and then I have the video. And I'll explain what I'm doing with MTCNN here. Now, separately, I could have gone from the fMRI to the latent space, and I'm using the same decoder, okay? And I'm going to try and argue that I can actually do reconstruction well. And of course, I could show you a bunch of these hazy images. These are not going to be clean. Don't expect an ATP here. These are going to be really hazy images. I could show you that, and I could somehow argue that those really are images, and you should take my word for it. But that's actually not particularly nice. It's qualitative. So what we actually do is to take a pre-trained neural network. So we don't train this. MTCNN is pre-trained. And we run that pre-trained neural network on the outputs of the encoder decoder applied to the video itself, or the map decoder applied to the MRI. So I'm going to apply the same MTCNN to both, and I'll look to see if I can predict objects here. In this case, for example, face or no face. So the MTCNN says, I saw no face in this set of video frames. And if the MTCNN also says that I see no faces in this set of fMRI frames, or conversely, both of them see faces, then that's quantitative proof or validation that I can actually reconstruct faces where there should be faces. And we can show that you actually get very, very good accuracy in being able to identify faces from both of these left and right paths. So this is kind of cool. So this is the ROC curve, and you can see that this is actually very, very statistically significant in where we predict, for example, things like faces using MTCNN from both the left encoder decoder and the reconstruction from the map decoder. So this is really cool that we can do this. And this is the final proof of what we're doing here. So these are raw reconstructions. So this is somebody's face, and you can see some. Well, so a lot of this is one of my students' work who finished his PhD and joined University of Cincinnati. And then what I wanted him to do was to put bounding boxes around the MTCNN identification. We haven't done that yet, but this is the bounding box roughly. So that's how we extracted this. So these are the two eyes, nose, and mouth. You can actually see this. So this is also what MTCNN picks out: two eyes, nose. And this was roughly the bounding box that MTCNN picks out. This one is a lot hazier. I don't know how MTCNN sees a face in here, but there's actually apparently MTCNN recognizes a face in this. So these are the kind of reconstructions we can do at this point. But this is incredible, right? So this is a point where we're actually reading people's minds as they're sitting in an fMRI machine. So this is sort of a very, very aggressive result that we think we're almost at the point of. Could we do better with the models? Absolutely. But I think the bigger advance has to come from a much, much larger training set. If we had a much larger training set, we could do this much better. So that's roughly what I wanted to talk about. I can talk about a lot more techniques on these things. So how we do. There are other abstractions here which have to do with graphs and graph alignment, which raise some really cool problems on what we call structural graphs and how we align structural graphs. I'm going to pause at this point, perhaps take questions, and Gabriela, if you want me to continue on some more, I'm
That
happy to
would,
do that as
yeah.
well.
Let's try to have some discussion. I saw that Fatima had another question. I wonder if your following explanations clarify that, but she was asking, Fatima, do you want to ask again the question? I don't know if it got clarified in the meantime.
Sure. Yeah, I was just wondering what kind of network you used from the fMRI to the encoded latent space for the videos.
Okay. So I
The
had
training.
that, and I might have skipped that too quickly. So, oops, sorry about that. So this is the map.
Oh, okay.
So it's got a bunch of GRUs and a dense layer at the back end.
Okay. Thank you so much. That was a very interesting talk. Thank you.
Thanks.
Thank you, Ananth. That's a very inspiring work. I have a few questions. Maybe
Please.
some of these might be naive. I don't know if Mark is in the audience. He's probably more experienced with this fMRI data than we are. So I see that in your final results, there are these comparisons that you're making with, these projections or predictions you're making coming in from the blue space and identifying what the person might have viewed.
Yeah.
And fMRI is considered quite noisy, right? In general.
Absolutely. Yes. Yes.
The models themselves perhaps are maybe not capturing all the nuances, and there's a lot to do with the model development also. That's the other side of the story. Yeah. So how do you think your prediction of this is a person with a hat or a certain scene, like you saw that there was quite a bit of variation and a lot of nuances were missed.
Yeah.
There could be similar kind of activity or stimulus that could, trigger similar areas in the brain, or the connectome could be similar. So how robust or these predictions are? I mean, I'm sure this is ongoing work, but I just wanted to see where you're.
No, absolutely. This is an excellent question, Dirisha. So we go through exactly these questions even as we do some of these things, and we try to answer as much as we can. I will be the first one to admit that most of the questions are unanswered at this point. But let me try to answer what you're specifically asking. So the question you're asking is something that we thought of, and I don't know if you caught that word deconvolution as I was talking about the second part of the presentation. So when we look at these MRI signals, they're in fact incredibly noisy, and in fact we don't even call them noise. So for example, I'm only reconstructing the image plane. I'm not doing anything with the audio plane. So in fact, even as the brain is processing both the audio and the visual stimulus to it, the responses are all mixed. They're all on top of each other. And so that deconvolution part is actually quite important, where we separate out what we believe are these different parts of these signals. And that helps a lot of robustness. The second part of the talk also tries to give some hints as to, it does not answer your question directly, but it gives you some hints as to why we pick out those nuances. In other words, different people watching the same scenes have very, very similar responses in terms of those representations that we talked about. So once you have deconvolved sufficiently, then those representations tend to be quite stable. In other words, that if you're watching something and I'm watching something, and I'm using those representations and I'm feeding those representations into that map, then more than likely I'm going to end up in those blue spots that are going to be close to each other. In other words, your blue spot is going to be very similar to my blue spot. So there is quite a bit of robustness built into this. There's, in spite of the fact that we have signatures, and the first part of the talk sort of contradicts my second part of the talk, in the sense that in the first part I said we are unique in how we think. In the second part, I said that there's a lot of similarity in how we think. they're actually not contradictory. In fact, I will mention something to Gabriela, which will pique her curiosity. So there's a SIGMOD paper that we've written, and that had to do with a lot of data that people release. So that paper actually caught the attention of the regulators in EU because EU releases a lot of these MRI data sets. And what that paper says is that I can uniquely identify people based on their MRI data sets. And so, of course, to somebody like Gabriela, the question would be, how do I then anonymize those data sets? In other words, if my signal was only in those 60 parts of the connectome, could I decimate those 60 parts and have they now become de-anonymized? Anonymized. And so that was the obvious question we asked ourselves. And the answer is unfortunately no. You decimate those 60, the next 60 will still be okay. They won't give you a 97% accuracy. They'll give you a 95% accuracy. So while those 60 are unique to us, the next 60 are also somewhat unique to us. So there is this very interesting thing that happens in our brain that is robust. We all have similar responses, but there's also unique aspects to our responses. So I'm giving a very weak answer to your question, but that's the honest answer I have.
Yeah, I think I see like even in that 60 features versus the next 60 features being important, I think there is this nuance to getting to high precision, right?
Yeah, absolutely.
To 90% of the precision or 80% very quickly, but the remaining 10% is the challenging part, I guess. The other question was, how representative were your data sets? As in, like the data, I know you had like certain 17, or I forgot the.
In the last data set, the last data set was a little larger. So I think it was about 30 to 35 patients. So the second one was 17.
Were there like, so, I mean, we worked with this data set in other contexts, but there is a lot of, I think, regulation in how data is accessed across geographical regions, and also there are some other restrictions. So perhaps I'm thinking it's not inclusive at this point. Maybe that's not what you're.
No, I think your question is well founded. So your specific question is, how randomized is that data set? And unfortunately, we have absolutely no way of controlling that. We don't do the MRIs ourselves. We actually get our data sets from third parties. Of course, we go through all of the usual HIPAA and this and that. But unlike, for example, HCP, the first data set was actually very controlled. So HCP is a very formal project. They have very nicely randomized samples. The other two data sets are not well randomized. They are quite localized. They are from one source, but that's the best we can do at this point.
Do you think that you could find some bias if you had family members, if they are localized?
Yes, absolutely. So there are results that we don't publish. So with 100% accuracy on a very small number of features, I can predict male, female.
Okay.
With close to 100% accuracy, I can predict family members.
Interesting. Yeah. Well, that's another application if you want to know which.
So we've always been a little wary of how somebody might misinterpret those results. And that's why we have never published that.
Yeah, makes sense.
But no, there's a lot of power here. And in fact, you know, if somebody is so inclined, the sequence of experiments I really wanted to set up was, you know, you can put kids in an MRI machine as they're playing video games. So the first part of my talk alludes to the fact that I can predict your controller inputs to the controller. So basically, in the first experiment, you let the kids play in an MRI machine or fly a plane in an MRI machine, if you will, and you see how well you can predict their control inputs. In the second experiment, you disconnect the controller from the physical plant, and you let them still play. But now they're still wiggling their controls, but the controls are actually generated from what you have inferred from their fMRIs. And in the third experiment, you take away the controller completely and see if they can still generate those inputs without actually moving their hands, and see if you can still play those video games with no input from the individual at all. This is not entirely new. Some version of this is actually being massively investigated when you talk of what the AR VR devices will be 10 years out. So this is sort of the big vision for the AR VR devices. But these are the kind of studies which will provide the basis for those kinds of devices.
There is a researcher out of ETH, I think, Mackenzie Matisse. I don't know if you know of her
No, I
work.
don't.
She's doing this with experiments on AR, VR video gaming
Yeah.
with mice in this control settings that you're talking about. So that you might find some of that work interesting.
No, absolutely. Yeah. So like I said, we are not the only group doing this. I think we have sort of been a little more ambitious in what we do. I think a number of experiments are a lot more controlled in the sense that they have a very specific outcome in mind. Can I predict this particular response from this particular input? I think predicting visual or image responses is, even after our results, ridiculously hard. And to the extent that we can make any progress at all is actually quite cool.
Thank you.
Thank you so much.
I didn't
It's
realize we
exciting.
actually went over
Hey,
our hour.
next time when we meet, I want to talk about this more. I was not aware of this side of your work.
Thanks, Gabriela.
Thank you so much, Ananth. And
My pleasure. Thanks for having me, guys. And please feel free to send me questions. If there's anything at all I can clarify, by all means, please.
thank you. Have a good weekend.
Thanks,
Thank you.
guys. Bye-bye.
Thank you.
Bye.